Good morning. I welcome you all for this lecture series in Mechanics of Solids course. So we have seen many constructions connecting the rivers, and we have seen many bridges and buildings. In these bridges and buildings, whenever there exists a load, there exists a deflection. So our today's topic is understanding beam deflection. This presentation introduces beam deflection. It defines its importance in structural engineering, real-world examples including bridges and buildings. Deflection limits are vital for serviceability and safety. Common beam types include cantilever and simply supported beams. So let us see what are the types of loads we have. We have concentrated load, uniformly distributed load, uniformly varying load, and all these affect deflection. The support conditions are pinned support, roller support, fixed support, free supports dictate beam behavior. And load combinations are like dead load and live load, wind and seismic loads are combined. These are all the load conditions for the beam. And the basic deflection equations for simply supported beam, we have PL cubed by 48 AI, and where P is load and L is length and elasticity, E and I is moment of inertia. So likewise, we have the formula for uniformly distributed load, cantilever beam. So methods of calculating deflection. So we have 3 to 4 methods. Those are double integration method, moment area method, and virtual work method. So double integration method derive deflection equations from bending moment equations and integrate mx to find slope. So further integrating the slope, we will get the deflection of the beam. Moment area method use moment diagrams to find the slope and deflection. Change in slope is equal to area of M by EI diagram. And the third method is virtual work method. Apply a virtual load to calculate deflection, where integration of moment by EI into dx will find the deflection of the beam. So material properties and section geometry. So modulus of elasticity of steel lies E approximately equal to 200 GPa, and GPa stands for gigapascal, and for aluminium we have 70 GPa, concrete we have 30 GPa. Moment of inertia for rectangular section is dh cubed by 12, and circular section is about 5 by 4 d square d power 4 divided by 64. Temperature, thermal expansion and contraction affects deflection. So what are the boundary conditions and continuity? Support types influence deflection behavior. We have seen different support types. One is fixed support, roller support, likewise. And continuous beams analyze using slope and deflection or moment distribution. Fixed end moments, calculate moments at the fixed support. These are all the three major boundary conditions and continuity. So we have to consider practical things that is available. One is deflection limits. So the code requirements to calculate deflection: creep and shrinkage, time-dependent deflection in concrete, dynamic loads, impact and vibration matter. So these are the practical considerations that is need to be considered. And we have certain case studies and conclusion for better understanding. Steel bridge gridder and the deflection analysis, concrete floor slab, deflection analysis shown, and accurate calculations crucial in structural design. Hope you would have understood what is deflection of beams. The slope, the major summary of this presentation is to find the slope and deflection of any given beam using moment, modulus of elasticity, moment of inertia, and to understand where the maximum bending moment happens, where the maximum deflection happens. Thank you all.